Hey guys, welcome back to another video. In this video, we're going to learn about geostationary orbits. Why are they useful? How do we calculate the altitude at which satellites need to be to maintain geostationary orbits? And how are they useful? So, first of all, we need to understand the properties of a geostationary orbit. So the first point is a satellite, an object that is in geostationary orbit. It needs to be above the equator and it needs to be above one fixed point. So let's say I want a satellite right above this point in my room. So I'm going to place the satellite, let's say 800 meters or 1000 meters above in altitude. And this is the point I fix to be the fixed point about which it is going to rotate or revolve around. So what's going to happen is as the Earth rotates, the satellite would rotate along with it in sync. It is not going to leave this fixed point. It is going to stay directly above this point and is going to revolve along with the Earth. Now, note one thing. This point that I mentioned, this fixed point needs to be on the equator. It needs to be on the equator. If it is in any other position rather than the equator, then it's not going to be in geostationary orbit. Why is that the case? Let's understand that. So if I have this tape, consider this to be Earth. I'm going to mark the top as North Pole, and the bottom as the South Pole. We do know that the Earth is actually a bit tilted, but let's not consider that and keep it simple. So I'm marking the equator. So south over here. So the North Pole is on top. Notice the North Pole is on top and the South Pole is at the bottom. And perpendicular to it is our equator. Perpendicular to it on the other side is our equator, right? Now notice one thing. If I revolve this Scotch tape around in that direction, what you're going to see is above the North and South Pole, it is rotating, right? Fair enough. So now let's say I have this marker, or let's take this finger as the satellite. If I have this point marked as the fixed point, I'm going to keep my finger exactly above this point and I'll let the Earth rotate. Now notice, as the Earth rotates, I can keep my finger exactly above the fixed point. However, if my finger was at any direction other than the equator, let's say over here, this finger would rotate, let's say, in this direction, and the Earth would rotate in this direction. So notice, if I fix this top point as our fixed point, and I let the Earth rotate, and I let my finger rotate, they are out of sync. My finger is unable to be above the same exact fixed point. So mind you, yes, after a period of time, it will come back to the same fixed position, but it will not stay in sync. Whereas if I had fixed a point on the exactly above the equator, it would revolve around it exactly in sync. It would not move away from the fixed point. So if I show that on a diagram, that is, if I have this point as my fixed point, our satellite is going to revolve directly about this point along with the Earth. However, notice, if I laid it over here and say this is the circumference you have to oscillate, orbit, it will go out of sync from the fixed point because Earth is rotating in this direction. And if I let my satellite orbit in this direction, it is not going to stay in sync with the fixed point. So that is an important attribute of a geostationary orbit. It needs to stay exactly above the fixed point and it needs to revolve around along with the Earth, right? Okay, second point is it needs to move from west to east in the same direction as Earth. You already know that Earth moves from west direction to east direction. So let's say north is above, south is on the bottom, and north, south, west, east. For me, this side is west. For you, I don't know if this is west. No, this is east. So this is going to be your west. So consider this to be the west and consider this to be the east. So Earth is actually moving from west direction to east. How do we decide that? So if I'm thinking about this point, if this is my home or this is my country, this point, and this is, as I mentioned, the west side and this is the east side, what we notice is as the Earth moves from this direction to this direction, that is from west to east, the sun, let's say, is in this direction. The sun is going to rise from the east direction. So the sun rises from the east direction and the sun is going to set on the west direction, right? So this side of the Earth is going from west direction to the east, and we can see that the sun is rising on the east and setting on west. This is why we can say that Earth, since sun rises on the east and sets on west, the Earth has to move from west to east to make that possible. So we know that Earth is also orbiting around something. That is, in our case, the star, the sun. So in our case, Earth is orbiting from west to east so that sun can rise on the east and set on the west, right? So taking that into account, we know satellite also has to move in the same direction to be above the same fixed point. So it has to move from west to east. Great. Third point, it has an orbital period equal to the Earth's rotational period of 24 hours. So notice, to be about the same exact fixed point, it needs to have the same 24-hour period. That is, it needs to complete one revolution within 24 hours so that it can stay about the same fixed point. Now, I keep repeating it needs to stay about the same fixed point, but why is that the case? Why do we need that? So let's say I'm transmitting any information to the satellite. Let's say I want the satellite to observe the weather, and I want the satellite to transmit that information to me. Now, the benefit of having it directly above you is there is no transmission delay. You don't need to figure out where the satellite is, calculate its distance, and then be able to take the transmit the information or take the information, receive the information. So no amount of tracking is required. So it removes the hassle, which is why it gets easier to monitor anything, the weather in a specific region or anything literally. So that is why having a satellite exactly above a fixed point is important, is helpful, right? So now let's look at a question. A satellite in geostationary orbit appears to remain above the same point on Earth and has a period of 24 hours. State two other features of a geostationary orbit. One, it remains directly above the equator, as mentioned, has equatorial orbit, and moves from west to east, as mentioned. So, okay. Now, one thing to understand is for this satellite to orbit, the satellite need to reach its velocity or orbital velocity such that Earth provides the centripetal force to revolve around Earth. We know from the previous video, Earth's gravitational field is going to contribute to the centripetal force. So the gravity itself is going to pull the satellite towards the center, providing the centripetal force. However, you may question, why is the satellite not falling towards the surface of the Earth? That is actually happening because the satellite at the beginning reached its orbital velocity. In case of circular motion, notice you need a certain orbital velocity to remain in that orbit. Similar to that, in our case, that satellite needs to reach the orbital velocity before it can continue its orbit solely dependent on the Earth's gravity. Therefore, there needs to be a thruster that provides that force and puts the satellite in that orbital velocity such that once that orbital velocity is reached, the satellite can orbit around Earth, since the Earth is going to provide the exact amount of force towards the center. So you have the two factors ticked off, that is in orbital velocity. Second, the centripetal force is provided by the Earth's gravity. Okay, so in this part we're going to see how the satellite, or at what distance the satellite needs to be to maintain geostationary orbit. That is, have the same period as the Earth's rotation, right? It needs to revolve along with Earth. So notice, for the satellite to remain in that exact orbit, it cannot be at any altitude. Because if you've watched the previous video, you've noticed that it needs to have a certain radius, sorry, not this one. It needs to have a certain radius to have a certain time period. So in our case, we know the satellite to remain in geostationary orbit needs to have a time period of 24 hours. So it needs to be at a certain separation away from the Earth's center such that this 24 hours of time period is achieved, right? So it needs to be at a certain altitude above the Earth's surface, right? So how do we find that? So we're going to find that using the Kepler's law. We found out that the r cube is equals to time period squared times gravitational constant times the mass of Earth divided by 4 pi squared. So now if you make time period the subject, you know the time period needs to be 24 hours. If you convert that to seconds, 24 hours into 60 minutes into 60 seconds, that is going to give you 86,400 seconds. So you also know the values for gravitational constant, you know the mass of Earth. So now you can find out the distance or the separation it needs to be at such that it can be in geostationary orbit. So you know the time period, you know the gravitational constant, you know the mass, and 4 pi squared is a constant. So now you will find for r, and you will see that that is the specific altitude you need for your satellite to be in perfect orbit or in geostationary orbit with respect to Earth, right? So this is the formula you can use to find the altitude or find the separation. Mind you, altitude is not the same as separation. I keep telling altitude, but altitude is measured above the Earth's surface, but the value you're going to get over here is from the center of the Earth. So if you are asked to find the altitude, in that case you have to subtract the radius from it. Okay, anyways. So in this case, we were using the satellite as an example, which has a 24-hour orbit. 24-hour time period. Now, in other cases, you might be asked to find the separation needed given any time period. Let's say the time period for that is 100 hours. So in that case, you will be asked to find the separation. How will you do it? Same formula. So you're going to use 100 squared times g times the mass of Earth divided by 4 pi squared, and you're going to get, if you take a cube root over here, you're going to get the radius or the separation for that object to be in orbit with a time period of 100 hours. So that's how you can find the distance. Now, there's an interesting part to this that I just added for no reason. You may think that, let's say, while playing cricket, let's say, for example, if you throw a ball, why doesn't it orbit around Earth? Why does it, fall towards the surface of Earth after a certain point? Whereas a satellite keeps orbiting. I sort of answered this in the previous part while talking about this, that it needs to reach a certain orbital velocity before it can continue its orbit around Earth. So even in this case, the answer to the problem is simple. When you're throwing the ball towards the stump, let's say, you're not throwing it with enough velocity. It's not that it is way too near the Earth's surface to maintain an orbit. It can maintain an orbit. But for that to take place, you need to throw it at a certain orbital velocity. So let's say we consider any ball to be thrown around the Earth's surface, near the Earth's surface, let's say. And what you're going to notice is you need to throw it at a certain velocity. Now, how do you find that velocity? Remember, from over here, the speed required to orbit a planet, in this part I had discussed, this is how you will find out the orbital velocity needed at that distance away from the Earth's center. So let's say I want to throw a ball from over here and I want this to orbit around Earth. Doesn't matter at what time period. I want it to orbit around Earth at this distance. So what I'm going to do now is, let's say the distance from the center of the Earth is going to be, I'm going to take the radius of Earth as the distance, and that distance is actually going to be 6,371 times 10 to the power of 3. That is your radius of Earth, most likely. Yeah, that is your radius of Earth. And 2, let's say I just considered it to be 2 meters above the Earth's surface. So if this is your Earth, this is your radius, which I considered to be, or the actual value is 6,371 into 10 to the power 3. And let's say I'm throwing the ball from this position, which is 2 meters above the surface. So I'm going to consider the radius. This is the radius. The separation to be 6,371 times 10 to the power 3 plus 2 meters. This is not actually going to do much of anything. But anyways, so I'm also going to take the gravitational constant, G. I'm going to take the mass of Earth, which is one search away. And now I'm going to find the velocity I need to throw the the cricket ball at, right? So now if I make velocity the subject, if I calculate all the values, what I'm going to get is 7,925 meters per second. That is 8 kilometers per second. So if I am at an altitude 2 meters above the Earth's surface, I need to throw that ball at a speed of 8 kilometers per second, which, mind you, is very fast. So if you have that amount of strength and you can shoot the ball at that speed, that ball is going to orbit around Earth's surface. Now, granted, we did not consider orbital decay, that is due to the air resistance. So we are not considering air resistance and any other factor. So granted, it is a void and there is no air resistance. If you throw it at 8 kilometers per second, it is going to orbit around Earth at an altitude of 2 meters. So I found this part a bit interesting, so I just added this over here. So yes, anything can orbit. If you can make it reach the orbital velocity, it is going to orbit around Earth. In an ideal situation, at least. Right. So, the next part I'm going to talk about is polar orbits. We started this video talking about geostationary orbits. In that case, the satellite needs to be directly above the equator, right? However, that's not the only kind of orbit. And that's not the only useful kind of orbit. We also need something called polar orbits. Now, what are polar orbits? Let's say this is North Pole, this is South Pole, and this is going to be a polar orbit. It's going to rotate along the axis of North and South Pole. While beginning this video, I took this example and said how if I take a point and I make it orbit, it is going to orbit out of sync. It is not going to be about the same fixed position. So in polar orbits, the difference is it's not going to be about the same fixed position. It's not going to stay above the same fixed position, right? That's the first point. So yeah, it is an orbit where the satellite is going to orbit about the axis of both poles, that is North and South Pole. So it's going to, if this is your North Pole and this is your South Pole, it's going to orbit like this. It is going to orbit like this, right? Okay, so it is not a geostationary orbit, meaning it doesn't stay above a fixed position. As mentioned, it does not rotate around the equator. It rotates around the axis of rotation. Okay, so it tends to orbit at lower altitude. That is third point. Fourth point, the time period is going to be lower. Why? No, remember the formula proportionality that r cubed is proportional to t square. So if your altitude is lower, your time period is also going to be lower. So in polar orbits, the altitude is lower, the time period is also lower. Now the benefit of this is, since the satellite is at a lower orbit, you can transmit the information a bit faster, since it doesn't take as long to reach that altitude above Earth's surface. In case of equatorial orbit, we saw that it needs to be at a certain height above the Earth's surface to maintain that orbit. Although, yes, it's directly above your fixed point, you do not need to find out where it is, but that amount of time needed to transmit the information might cause a lot of information loss, a lot of data loss, which is why it is also beneficial to have polar orbits where the orbit is actually lower, where the information can travel faster. Even though you need to track where the satellite is, you can transmit the information a bit faster. And there is less likelihood of data loss. Okay. So if we try a question over here, suggest one advantage and one disadvantage of the use of geostationary satellites compared with polar orbiting satellites for communication between points on Earth's surface. So the advantage of using geostationary satellite is, one, as mentioned, no tracking is required, since the satellite stays directly above one point on the equator and it orbits with the same speed, with the same angular frequency as Earth. So you don't need to do any bit of tracking. The disadvantage though is the orbits are longer, hence further from the Earth's surface, because the orbit is 24 hours, right? So it is further from the Earth's surface, the separation is much bigger. Therefore, there is a larger delay or greater attenuation. You're not going to understand what attenuation is, but just understand there is a greater delay of information being transmitted from the Earth's surface to the satellite, because the time period is very large, 24 hours. So the separation, the altitude the satellite is at is also very large, which is why there is a lot of data loss or a lot of time is required for the data to be transmitted. Whereas if it is a polar orbit, it has a lower time period. We set the time period to be lower and keep it at a lower altitude. The benefit of that is we can transmit the information faster. So those are the 2 points, and that is what geostationary orbits are. And that is it for this video. See you in the next one.